Welcome to the module Temperature Dependence of Internal Energy and Enthalpy. In this module, we will explore how internal energy and enthalpy change with temperature, focusing on the role of heat capacities. Let's recall how the internal energy and enthalpy of a system depend on temperature. Understanding these dependencies is crucial for evaluating energy balances in various thermodynamic processes. We begin by examining the heat capacities at constant volume and constant pressure, denoted as CV and CP respectively. These quantities describe how the internal energy or enthalpy of a system changes with temperature. For any system or substance, the relationships are as follows. The heat capacity at constant volume, CV, is defined as the partial derivative of the heat added at constant volume, QV, with respect to temperature T, and is also equal to the partial derivative of internal energy U with respect to temperature T at constant volume V. Similarly, the heat capacity at constant pressure Cp is defined as the partial derivative of the heat added at constant pressure Qp with respect to temperature T, and is also equal to the partial derivative of enthalpy H with respect to temperature T at constant pressure P. Now let's focus on ideal gases. For an ideal gas, the dependence of internal energy and enthalpy on system parameters is significantly simplified. The infinitesimal change in internal energy du always equals Cv times dt. Likewise, the infinitesimal change in enthalpy dH always equals Cp times dt. It is important to remember that the heat capacities Cv and Cp are in general temperature-dependent properties of a system or a material. This means that they can change with temperature, adding complexity but also accuracy to our analysis. In many cases, instead of the heat capacities of an entire system, we use molar heat capacities, denoted as CVM and CPM, which are the heat capacities per mole of a substance. Let's discuss how can we determine the change in internal energy and enthalpy with temperature while taking into account the temperature dependence of heat capacities. The general formulas for the changes in internal energy, denoted as delta U, and enthalpy, denoted as delta H, when the temperature changes from T1 to T2, are given by integrals. Delta U equals the integral from T1 to T2 of Cv as a function of T by dt. Delta H equals the integral from T1 to T2 of Cp as a function of T by dt. Now, if we know the heat capacities of a system Cv and Cp as functions of temperature, these equations with integrals allow us to determine the changes in internal energy and enthalpy of the system as the temperature changes. Let's now consider what happens if the heat capacities Cv or Cp are independent of temperature. In such cases, the integrals we talked about earlier simplify to much easier forms. If Cv does not change with temperature, it holds that delta U equals Cv multiplied by the difference between T2 and T1. Similarly, if Cp is constant, delta H equals Cp multiplied by the difference between T2 and T1. This means that if and only if the corresponding heat capacity is constant, the change in internal energy or enthalpy can be calculated by simply multiplying that heat capacity value by the temperature difference. This is a very useful simplification, but remember that it only holds when Cv or Cp are indeed constant, which is not always the case, especially over large temperature ranges. So remember, when dealing with temperature changes, always check whether the heat capacities are constant or temperature dependent. This will guide you on whether you can use these simplified equations or need to resort to the more general integral forms. As a final note, by applying the same equations to molar heat capacities, we can calculate changes in molar internal energy or molar enthalpy. Always pay attention to this distinction and do not neglect to differentiate between the change in the internal energy or enthalpy of an entire system and the change in the molar internal energy or molar enthalpy of a chemical substance. I would also like to draw your attention to the fact that the difference between the properties of an entire system, such as internal energy and enthalpy, and molar quantities, such as molar internal energy or molar enthalpy, is not only quantitative but also qualitative. The internal energy and enthalpy of a system are extensive properties and depend on the size of the system or, in the case of chemical systems, on the amount of each substance in the system. In contrast, molar internal energy and molar enthalpy are intensive properties. They characterize individual substances present in the system and depend on the state of the system as described by its intensive properties rather than its size.